The final letter in our VPIGS mnemonic is S for surface tension, and we're going to look at surface tension forces. If we had an interface between air and water, continuous across like this interface is in tension, and that tension depends on the chemistry in fairly complicated ways. For example, if we introduce some soap into this water, that will change the surface tension quite dramatically. We're not going to worry about that chemistry in mechanical engineering. We're just going to remember that it's there and that it's important. So if we zoom in on a little segment out of this surface and we pull it out as a free body diagram, there's that little chunk of surface. There's our control volume that we drew around it. And there are going to be surface forces acting on both ends of this little chunk of fluid surface. If we imagine that that surface extended into the page and back out of the page, some length L, then those surface forces that act over that length L would be equal to the surface tension, sigma, times that length. So sigma is the surface tension. It has units of newtons per meter, so that when we multiply it by a length L in meters, we get a force in newtons. And sigma is often very small. Even for water, which has one of the highest surface tensions, we only have about 0.073 newtons per meter for a water-air interface. So usually surface tension forces are really small. So let's consider what we've got inside a drop of water, just as an illustration. Consider half of the drop of water. It'll have surface tension acting around the edges, and it will have pressure acting over all of the area in between. And those forces will be in balance unless that drop is changing its shape and deforming. So pressure times the cross-sectional area, pi d squared over 4, must be equal to surface tension times the circumferential length, pi d. If we rearrange that, we'll get that the pressure inside that drop will be equal to 4 times sigma divided by d. So that says that the higher the surface tension, the higher the internal pressure will be compared to the pressure outside the drop. And the larger the drop, the lower that pressure will be. This radius of curvature will be lower, and there'll be less surface tension pressure effect. So if we calculate that pressure, it'll be about 0.3 pascals for a diameter of 1 meter. So if we had a 1 meter drop of water, the pressure difference would be pretty small. Remember that 1 atmosphere is 100 kilopascals. So this is a very small pressure difference. Surface tension is going to be pretty unimportant at large scales like this. But if we go down to the scale of the video we looked at, we would get to about 300 pascals for drops that are 1 millimeter in diameter, or about 300 kilopascals, 3 atmospheres, for drops that are about 1 micrometer in diameter. So somewhere along the way from large-scale flows through still relatively large drops of 1 millimeter on the way down to drops in the micron-sized range, we're going from surface tension being unimportant to being on the same order as other forces that are acting on the drop, to being the dominant force that's controlling the drop and its behavior. And that's why really small drops are all spherical. All the other forces much smaller than surface tension. So surface tension is the last letter, the last S in our VPIGS mnemonic. And those are the forces that we need to rely on when we're assessing the magnitude of different forces in fluid flows.